All right. Well, good morning, chemists. Um, Welcome to the A-Level Chemistry Masterclass series. I'm Graeme Matthews with Empower My Intuition. So what I want to do is just welcome you aboard to the Masterclass series, tell you a little bit about it, why I'm doing what I'm doing. So the reason why, the very first question people have is, well, what is the Masterclass series? The Masterclass series in A-Level Chemistry is just this. It is a weekly help session where I go over difficult topics that you may see on the upcoming A-Level Chemistry exam, as in the end of unit or the mock exam or the UCAS exam or your final exam. This is what it is. It occurs once a week. So if you're watching this on my YouTube channel or if you're watching it on my Facebook group, then below the video link will be the time of the weekly help session. Now, it's just once a week. Time is going to be below the description on my YouTube channel or on my Facebook group or on my Instagram group. In other words, on social media, look down below, all right, and you will see the time of the next meeting if you want to join it live, okay? So this is what it is just a weekly help session where I help A-Level chemistry students prepare for the upcoming tests, exams, UCAS, whatever, okay? Now, the next question I have, I'm always asked is this, like, well, why exactly are you doing this? I mean, you aren't charging for this, you're not making any money on it. What is the catch? Well, if you receive the email from me inviting you to this session, then I said in the email that I don't promote anything in these help sessions. So I'm not going to mention ebooks or work with me one-on-one directly or group sessions or my Facebook group or the online courses. None of that. This is completely marketing free. All right, it's a completely free session once a week. It's not something I do and then I say, oh well, hey, I can market to these people. No, this is for my subscribers, totally free once a week. The reason why I do it is because, and I know at the time of this recording, we're coming out of the COVID-19 pandemic. So this is going to be the post-COVID-19 era that we're in. I believe, and I know this sounds cliche, but I truly, honestly believe that education is the great equalizer. And so, having said that, I want to make sure that everybody gets a fair shot at getting a good quality education. And so, if you take an A-level chemistry, you're thinking, yes, you did well at GCSEs, and you're looking forward to going to university. And so, you take an A-level chemistry as one of these bridging subjects that you need these prerequisites in order to get into the university of your choice. So, having said that, I also believe that the face of education is going to change, meaning that, well, when I was in university a long time ago, I had hair down to here and an earring type thing. All right. It was distance learning, and this was when people would they would record the lessons, and then the students who were distance learning students, they could actually, and I'm going to date myself now, they could actually pick up a Betamax or a VHS recording of the lesson. And then we moved on to e-learning, like the CD-ROMs, e-learning, the very basic websites that you had. But times have now changed again because of the COVID-19 pandemic. You're thinking now people are live streaming. So maybe you're sitting in a class and it's being live streamed, or maybe you're at home during a lockdown, it's being live streamed. And so it's progressing along a little bit, isn't it? From the day of like the video recording that you could pick up on VHS to like CD-ROMs, DVDs, to online courses, to watching a class on your desktop, on your laptop, tablet, all right, to now you can actually live stream a class. Well, that's all great, But what I wanted to do, and this is the purpose behind this one, is I wanted to make sure that everybody had a fair shot. I want to level the playing field. So I thought, yes, in my subscriber base, you could be one of the students that you want to work with me one-on-one directly, or you want to work in a group, or you want to work in a Facebook group, or you want to take one of my online courses. Yes, but on the other hand, maybe you won't. Maybe you don't want to work with me one-on-one directly, or in a group, or in a Facebook group, or take one of my courses. You don't need that. It doesn't fit you. How you consume the information is up to you, isn't it? So you're thinking, yeah, I don't need all of this stuff, Graeme. So therefore, all I want to do is I just want a bit of help once a week. And maybe I don't have all the technology, like the latest phone or laptop or tablet, or maybe my parents don't want to invest in one-on-one tutoring or whatever. The reason is maybe I don't want to take an online course. I just want to pop in once a week and have some good quality teaching, some good quality education. And this is where this comes in. So this is where the masterclass fits into that workflow, if you would, is this. It's that if none of the other products that I offer work for you and you're thinking I still want help, then by all means, show up once a week and I'll go through some difficult questions with you, some difficult concepts. Now, having said that, it is student driven, right? And so I'll put this up here, okay? If you want to contact me directly, say, next week, do you mind going over these types of problems? Well, then this is my email address here. And so you're thinking, all right, it's just G Matthews and here at EmpowerMind. That's my company name. .co, move it out the way, .uk. So like I said, I'm not going to promote anything in these masterclass series, but this is my email address. And so if you're thinking, hey, really great, next week, do you mind going over this topic? Then fine. All right. And obviously my website is empowermind.co.uk. But like I said, I'm not going to market at all in these sessions or send out sales emails, to subscribers. No, it's just going to be pure teaching. All right, then. So here we go then, chemists. And so on this one then, all right, on this one, I need to get my pen ink down a little bit thinner here. What I wanted to do is I wanted to go over time of flight calculations. All right, so having said that, very first thing I want to do then is give you an overview. All right, an overview of where we are, and how I teach it is this. Now, I always teach to the student perspective, meaning that, I come up with little mnemonics, strategies, shortcuts, anything you need in order to get you through the question here. So this one here at Chemist, this is how I teach, right? I call this VIADD. Now you may have seen this, you may not have seen this. All right, it's one of these silly little mnemonics, but it sticks in your mind, especially when you're doing the question. All right, so you're thinking this one here, right? Take a look. So VIADD, all right. Well, V is vaporization. Now, yes, I was trained back in the States. I was educated back in the States. And so you will see a lot of American spelling come in. I do try to catch it as often as I possibly can, put the British spelling in, but there's vaporization with a Z. So these are live, chemists. This is not, scripted. So yeah, vaporization with a Z. And then ionization. Caught at that time. All right. Acceleration. Drift, detection. All right, so here we are then. Think of this one. This is the phrase that I tell my students: Victor is a daft duck. All right, so Victor is a daft duck. Yeah, I know it sounds silly, but on the exam, you're thinking, right, here we are. Question. This is like a 3-mark question. Victor is a daft duck. Got it done. All right, then. So here we are on this one then. All right, my sample is going to come in from hypodermic needle. And so this one here, this is the vaporization. Okay, so what you're thinking is, chemist, is this, is that, yes, you need to have the sample vaporized because it doesn't work if it's in the liquid state. It's got to be in the vapor state. So because you need the molecules, you need the sample, the atoms, the molecules to go down the time of flight tube. They can only do this if it's being vaporized, okay? So you're thinking, very first point is that it has to be vaporized, all right? So if it is a solid, for example, then you would put it into a solvent and then you would vaporize it, and they vaporize it by putting it in, by passing it over a small heater, and that's going to vaporize it into the gas phase. Now, having said that, you now need to ionize it. Now, I will talk about the two different types of ionization here, but ionization is this one. You've got to remove a valence electron, and so you end up getting a +1 ion and the electron that you took off. Now, at A-level chemists, you're always going to see it be the +1 ion. So at A-level, it's always going to be a +1 ion. All right. Now, this is the ionization bit here. Right, over here then, look, there's two types of ionization. The first one is electron impact. This is the one that, quite honestly, you will see 99% of the time, electron impact. And what it is you have a high-powered electron. If they ever ask you, there's a high-powered electron, and it's going to remove, it's going to knock out a valence electron. And so you end up with the +1 ion. Now, this one, chemists, electron impact is the one that you see about like 99% of the time, right? This is the one, you'll see this for elements. We'll do loads of questions today, right? Elements is one that you normally see this one with, or anytime that they have a small molecule that undergoes a fragmentation pattern, which we do in year 13, molecule with a fragmentation pattern, okay? Try to squeeze fragmentation pattern down the end there so we can actually see it. Hold on. A little bit better. Now, and the reason why you look at the fragmentation pattern is so that you can see, you can determine the structure of the molecule. Now, the other one that you see is electrospray. So down here then is electrospray. And so electrospray ionization, probably I would say about 1% of the time, they'll ask you to talk about electrospray ionization. And with this one is when you add a proton to the molecule. So for example, right, here's my X in the gas state, and I impact it with a proton, H plus, and you end up with XH plus in the gas state. Now, chemists, do we notice how it's positive one, whichever one you use, if you use electron impact or if you use electrospray ionization, you always end up with a positive ion. Now, electrospray ionization is really good for large molecules. And the dead giveaway in this one, chemist, is that these are normally like biological molecules, like molecules used in biology and everything else, because you don't want to break the molecule apart. What you want to do is keep it intact, so you get the only thing you can get from electrospray ionization is you can get the MR of the molecule. So you don't break it apart. Like electron impact, you break the molecule apart, right? You don't break it apart. Electron impact, you've got the element, you've got the molecule, right? You're going to break the element goes down, the time of flight 2 + 9. The molecule you break apart into smaller molecules or fragments of molecules, and you look at the fragmentation pattern. Whereas with electrospray ionization, all you want to do is just get the MR of the molecule. You're not looking to do any structural identity with it, all right? Now, here we are then with ionization. So ionization here, I'll move this down a little bit for you chemists here, look. So you've either got electrospray or you've got electron impact, like this. And then, I'll move this down just nice and neat. Then you've got the acceleration bit. Now, the acceleration bit, chemists, is kind of easy. All you got to do is acceleration is hold on, put down, right. Let me call it a sample. The sample, because then it could be electrospray, it could be electron impact. The sample is passed. No, let me call it an ion, because then it would be better off if I called it an ion. Hold on. Right. Right. The ion is passed between two oppositely charged plates, like this. Now, when you do this, what you notice is this, right? And if they ever ask you to explain it, we just go, right, look, two plates like this. Here's my ion in the gas state like this. Obviously, this plate's going to be positive. This plate's going to be negative because the positive ion is going to be attracted towards the negative plate, right? Now, you then go down the drift tube. So you may see this as obviously charged plates, or you may see it as like oppositely charged electric fields. The exam boards are moving towards the charged plates. But you may just see obviously charged electric field. Okay, now then. The ion then goes down a drift tube. Now, when it goes down a drift tube, chemists, what happens is this, is that the ions, they separate out. What I'm going to move board up. The ions separate out based on mass. Now, the important thing to keep in mind is that all ions have the same kinetic energy. So when they enter the drift tube, right here, see like the flight tube, this is also known as your drift tube. When they enter this drift tube, then what happens is that they've got the same kinetic energy coming in, all right, which means that they separate out based on mass. Now, what happens is the lighter ions travel faster, so they arrive at the detector first. And the heavier ions travel slower. So they arrive at the detector last. Right? Now then, this is because, obviously, you know, kinetic energy from GCS physics, kinetic energy is what, 1/2 mv squared. And so if my kinetic energy is constant, which we said it was coming in, then if my mass decreases, as in it's a smaller ion, all right, then the velocity has to increase. All right, hold on. The velocity has to increase in order to balance everything out. Okay, so you end up with this increase in velocity. Right, this is the reason why, if anybody ever asks you on the exam, you go, well, because kinetic energy is 1/2 mv squared. And so therefore, if the kinetic energy is constant, if the mass decreases, the velocity has to increase in order to keep it constant. Whereas if the mass increases, because it's a heavier ion, then the velocity decreases. Now, the last bit, so the ion goes through the flight tube, the drift tube, they separate out based on mass. And then the last thing, chemists, is the detector. Now, this is the bit that we'll spend a bit of time on, because this is the question that they like to ask. Is always having to do with the detector, okay? So this bit, I'll even highlight this bit, you know, because you're thinking, right, they may mention the drift tube because they want to know, do you know kinetic energy is 1/2 mv squared and the proportionality I just put over here? Or the other one they like to ask is the detector one. Now, the detector one, all right, is here. All right. Get my pen back here. Is this one? Look. It's a positive ion travels down the drift tube. Right. Now, got to keep in mind it's positive ion. The ion hits the negative plate of the drift tube of the detector plate. And then, and this is the bit that they're going to ask you about, an electron is transferred from the detector plate to the ion, yeah, causing a current to flow. All right, so my board's got to catch up with me there, chemist, but here we are, look. I'll do it in pink, right. This is the bit that you got to put in. You got to put in that the electron is transferred, okay, from the detector plate to the ion. So they want to see the electron transfer, right? All right, causing a current to flow. Now, having said that bit, you then go, right. Next thing then is, I just hold on. Next thing is that you're thinking, right, oh, did my board update? I think my board updated. Look, so the next thing then is the size of the current is proportional to the abundance of the ion. Now, let me just clean this up a little bit. All right. All right, hold on. Just let me clean this up, chemists. All right, I did some highlighting there. So just let me clean this up right there. Don't think I like the highlighting. So just let me clean this up real quick. Like I said, we do these live, all right? Is transferred. Plate to the ion. All right, we clean this up and then we'll do something else. Hold on. Causing the current to flow. Now, this bit down the end here, I'll just put a box around it. Look, the size of the current is proportional to the abundance of the current. Yeah, so what this means is that the more ions you have hitting the plate at that time, well, then you'll get a higher current flow. You'll get more current flowing. More current flowing means that the abundance of the ion can be determined. So what you see is this bit. You see this. So this is how you get, you know, your typical mass spec, you know, like percentage abundance like this, and M over Z values, okay? So this bit then gives us the overview of the mass spectrometer right there, okay? Which is a good question for them to ask you about, all right, on any test there. So what I wanted to do then is, I wanted to do some problems. So before I move on, the detector plate at the end, can I put down, this is for my A-star chemists, as in all of you. They're going to ask you a question about the detector plate because it is quality of language. All right, meaning that they're looking for you to mention the, you know, like ion, detector plate, electron transfer to the ion, and then size of the current is proportional to the abundance of the current, all right, of the ion. Now then, what I thought we'd do next then is, I thought, hold on, ding, 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 ding. Let's do some problems, all right? So hold on, I have to get a drink of water here, because we do these live, chemists. Every week, these are done live. And so if there is a topic you want me to cover, then please, by all means, do so. Email me in the address I gave you. All right. Somebody asked, well, do I record these live streams? The answer is yes, I do. And the recordings are obviously up on YouTube, or if you go to my website, they're also listed there. And so you can look at these at some later date. Now, here we are then. It says, identify the species responsible for the peak at M/Z52. Now, this is the one, chemists, that you're thinking, yeah, it looks easy, doesn't it? But is it? It's a trick here. Now, look. Oh, hold on, I'm going to wait. We always do these live, okay? So A right there. Now, all you got to do on A then is the relative atomic mass. Hold on. The relative atomic mass then is just going to be its percent abundance times mass and percent abundance times mass. And you just keep on going until you've used up all of the information given. For example, 50, 52, 53, 54. I'd have 4 of these percent abundances times mass. So then here we are. Percent is, the very first one is what, 4.3. Okay, and let's see, the mass is 50. And then you've got 83.8, and the mass is 52. And then you've got 9.5 times 53, and 2.4 times 54. And obviously, I've got to move it from a percentage to, well, a decimal. It's going to divide by 100. All right, then. So we do these live, chemists. And so here we are. Hold on. Pull out my trusty calculator here. About 20 years old. Here we go. Hold on. 4.3 times 50 plus 83.8 times 52 plus 9.5 times 53 and 2.4 times 54. All right. Divide that by 100, and I'm going to get, now, the actual value on my calculator, chemist, is pen is 52.057. But you'll notice that they always ask you for AR values, like on the periodic table of your exam board. They're always given out to 1 decimal place. And so therefore, if you wrote down 52.1, hold on, that's supposed to be 0.1. Do I clean that up a little bit? 52.1 AMU. All right, so green pen, got this one right, like this. Now, so this one then is A, all right? So it says right here, part B, identify the species responsible for the peak at M/Z52. Now, chemistry, so why I teach this one is this, right? I always point out the tripwire. So this one is a tripwire question. You'll see this in multiple choice questions on your exam, all right? Because you go, oh, hold on, Graeme. I know what the answer is. I know it's just chromium 52, right, isn't it? I mean, it's like, it's just chromium 52. All right, done that. Move on. No. Because well, technically you could put down 27 protons, but recall we said in the previous tile, we said that it's a positive ion that goes down the time of flight tube. So this chromium-52 atom is not the correct answer because you need to put in a positive 1 charge because it's a positive ion that goes down the time of flight tube. So right here in green, all the colors of the rainbow today is this, look. The positive ion is what is detected by the detector plate. Now, didn't we say in the previous tile, we said that the detector plate was negative, so you get the transfer of an electron from the plate to the ion. So in this one, chemists, yeah, you think, nah, got to be careful now, right? Tricky, yeah, tricky, right? Okay, then. All right, now, part C, it says, which ion will have the shortest time of flight and reach the detector the fastest? Well, C then is just going to be the lightest ion. All right, so I'm looking at the data right here. It's got to be 50. So come down to here. The one that's going to travel the fastest, we said, is the lightest ion. Now, which again, chemists, you're thinking, it's just not chromium-50, is it? No, it's the +1 ion. All right, because, and I'll extend the arrow down to here, the positive ion is what's detected by the detector plate. All right, so 3 for 3. Okay, now this one here. All right. Oh, I got a chromium-54 and I got chromium-50, and they want to know the time of flight of chromium-50. Okay, so this one came. So look, how I teach it is this: is that you've got to stop and think. Say, well, why are they really asking this question? They're asking this question, no pun intended, because we're talking about time of flight, but to separate you out based on your ability to use algebra to get the right answer. Okay, so they'll always put one of these questions, they'll always put a time of flight calculation question like this on your end of unit test or on your UCAS, your mock exam, the final exam, okay? Because what they want to do is they just want to separate you out into those students that can apply a bit of algebra. That's all we need is a bit of algebra. You learned this at GCSE. Okay, so I've got chromium-54 and I've got chromium-50. Okay, and do this live. So let's go up here. I've got chromium-54 and chromium-50 says time of flight of chromium-54 is what, 1.486 times 10 to minus 5. Okay, hold on. My ink's going to sink right now. Chromium-54, the time was what, 1.486 times 10 to the minus 5. All right, then. So here we are. Let's have a look at this one. So chemist, on this bit here, right, I'm going to say that, trying to get my ink to sink. I don't know why I just want to sink right now. Look, say this. We know going down the time of flight tube that the kinetic energy of chromium-50, hold on, what happened? Right, hold on, time of, here we are, right, it's done right, got it. Right, the kinetic energy of chromium-50 full must be equal to the kinetic energy of chromium-50. Yeah, it has to be, because they got the same kinetic energy when they went through the electric field or the differently charged electric plates. Now, having said that, then you know that 1/2 mv squared for chromium-54 must equal to 1/2 mv squared for chromium 50, right? So over here, I'm going to say set the kinetic energy for each ion equal to each other. Now, I can cancel out, and I'll cancel out in red. Look, you can cancel out the half. All right, because it's a constant on both sides. And let's see now. Here we are. So I can now, I'm going to put this over here. I'll doodle this down here so we've got a bit more real estate on the digital board here. Look. So you've got M of chromium 54. Can write that a little bit easier there. Look, the mass of chromium 54 times the velocity of chromium 54 squared is equal to the mass of chromium 50 all right, times the velocity of chromium 50 squared. Right, all I've done is I've just taken this and I just put this down there and I just put in the chromium 54 and the chromium 50. Now, next thing though is that you know that the velocity is distance over time. So right, now all I'm going to do is I'm going to substitute in. All right, got to keep my board updating here. Substitute V is d over t in for V in the equation. Now, having said that, chemists, this means over here, then I've got this. Look, I've got the mass of chromium 54. Whoops. Trying to get this looking nice and neat. My board's going to have to update in a minute. All right. The mass of chromium 54 times the velocity. Whoops. Oh, there it goes. Brilliant. Right. Just updated. Okay. Good, good. Try to get nice and neat for you. Look. The mass of chromium 54 times velocity is distance over time squared is equal to the mass of chromium 50 times distance over time squared. All I've done is I've just substituted in velocity is distance over time, but it's going down the same flight tube. So D is constant. So I've now got this. I can cancel out, if I change over to red, I can cancel out the two D's here. And so what I've got is this, is I've got this. So I've got the mass of chromium 54 over T squared for chromium 54 is going to be the mass of chromium 50 over T squared of chromium 50. And I'll try to clean this up a little bit here, okay? Now, like this. Right, now then. You see this equation here, chemists. This equation here is the one that you need to know. Right. You need to memorize this one. So what I'm saying is this. And this is what I tell my students, look, on the exam, you only have so much bandwidth. Meaning, it's only so many pieces of information you can put into your mind. There's only so many calculations you can do, so many like strategies for solving the problems you can have. And so if you're mathematically, you know, like you love math, we go, well, great. Let's just derive it on the exam, on the day of the exam. On the other hand, if you're thinking, no, to be honest with you, probably not, well, then memorize it. Okay, so up to you on that one, all right? So this one then, now we can solve the actual question, because I believe in the actual question, what they want to know was the time of flight to chromium-50. All right, so it is this one here. Right, I'm going to solve for T of chromium-50. All right, then here we go. All right, now cross multiply. So I'm going to get the mass of chromium-54 over T squared of chromium-54, all right, cross multiply, times T squared of chromium-50, okay, must equal the mass of chromium-50. So all I've done is I've just brought up this over to this side here. Now, meanwhile, I'm going to multiply by the time of chromium-54. So my board is in the process of updating. Hold on. So look, I'm going to have times this by this one here. And let's divide through by the mass of chromium-54. Now, the reason why I did it this way, I broke it down for you chemists, is because, well, I did math 38 years ago. And I did like symbolic math, like it's like look at it and you move it around in your mind. I think today you don't do that anymore. You use those triangle things, which do my head in. But again, teaching this in a way that whichever way you learn math is the correct way because it works for you. All right, as long as we all end up with this one here. Right, so all I've done then is a quick recap is I brought the T squared of chromium-50 up to this side, multiply through by T squared of chromium-54 divided by the mass of chromium-54, and I got this. So the T squared of, hold on, the time of chromium-50, I just need to erase this bit. Is just the square root. Like this. Yeah, right then. So I do believe they gave us the value for T. Hold on. Where did my value for T go? Oh, yeah. 54 is what? 1.486 times 10 to the minus 5. And to this one then, no. Here we are then, chemists, like this one. And so you're thinking on this one then, chemists, right? First off, you may have noticed how I just substituted in 50 over 54 like this, and there's a reason for this, okay? And again, chemists, this is one that on the exam you can save a bit of time because you don't need to know the mass of chromium-50 precisely in grams or in kilograms because it's relative to each other, right? So you're thinking the mass of chromium-50, I mean, even if we used Avogadro's number, converted it over to kilograms, and then did the same trick on the bottom with chromium-54, used Avogadro's number to get it from grams per mole to grams per atom, and then divided it by kilograms to get kilograms per atom, the two the values would cancel out because it's the mass is proportional to each other. So this is why I can do this. I can put down here, I can put down here the relative masses are proportional to each other. So we don't need to convert. Now then, right. So this one saves you a bit of time on the exam then. And so now the time of chromium-50, well, let's take a look. Okay. It's going to be, hold on, calculator here. I always do these live. 1.486 to the negative 5. All right, times 50 divided by 54. All right, take the square root of that. Hold on. And I got, no, I think let me type that again. Hold on. So you got 50 divided by 54. Yeah, is this times, all right. Oh, I forgot to square it. 1.486 to the negative 5. Got to square that. Now, if I take the square root of it, it's going to come out. See, like I said, Cam, so I always do these live. So therefore, you know, it's real. All right. So, ding, 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 486 to the negative 5. Yep, done that. Hold on to square this. Right, there we go. Got it. Got it. So I got, what, 1.428 times 10 to the minus 5. Now, having said that, chemists, let's take a look. The original one, where's my original data? All right, the original data was 1.486. So therefore, the chromium-50 should have been, because it's a lighter ion, the time of flight should have been less. The fact is coming in at around 1.428 times 10 to the minus 5 sounds good. Okay. Now you see how I paused there, right? I like took the values in the calculator, and obviously, you know, to make sure I typed it in right. But I thought the time for the chromium-50 has to be less than the time for chromium-54 because it is a lighter ion. All right then, so I wanted to put that one in because that is your typical question that you will see. You'll always see one of these questions where they ask you to manipulate the kinetic energy equation. And really, chemists, there's not too much that they can ask you for. So where's my, you see my kinetic energy equation there, 1/2 mv squared. Well, the only thing they can ask you for is they can compare the two time of flights, which we did with this one. All right. On this equation here, you can compare the two time of flights, or maybe they'll ask you to calculate the mass of the other ion. There's not too much they can do because the distance has to be the same. The kinetic energy has to be the same. Okay, so there's this one. All right then. Now, I also thought we'd have a little look at, all right, an actual past paper question here, okay? So on this one, let's take a look. So this one here, we'll do this one live, okay? So here we are on this one then, chemists. Now again, chemists, look, notice how what you've got is, I'll do this in blue. I always point this out to my students, 3 marks. So I always say, read the point value. As in, if it's 3 marks for the question, you need to have 3 marks in your answer in order to get all the points, right? Now, explain how ions are accelerated, detected. Now, the abundance determines the time of flight mass spectrometer. Right. So you're allowed to use bullet points on the exam. And so accelerated, I would say the positive ion, right, in the gas state is passed through to oppositely, hold on, I think I can write oppositely, hopefully a little bit better than that. Is my board going to update? I think my board's about to update. To oppositely charged plates. Yeah, so here we go. This is the one that we had, like this is your negative plate and that's positive. Here's your negative plate and here's your ion going through the plate, right? Passing through the plates. All right, 2 oppositely charged plates, or if on your exam board they say, that they're using electric field, you go, okay, well, 2 opposite electric fields, right? So this is how they're accelerated. And so they gain the same kinetic energy. All right, so this bit's key. They must have the same kinetic energy when they leave the acceleration area, okay? So number 1, how are they detected? Now, they're detected by when they hit the detector plate, right, an electron, and this is the key bit, okay? An electron is transferred from the detector plate to the ion, causing a current to flow. All right, now trying to see if I can get my board to update here. All right, hopefully it's going to update so that we can move on. All right, now then, key bits and chemists, key bits, right? I made a slight saying, right. The electron is transferred from the detector plate to the ion, all right? This bit becomes important, right? You have to indicate that the electron is transferred from the detector plate to the ion, causing a current to flow. And they're looking for the word current. Okay, now then, you're thinking, and out of space here, so I'm going to say, how is it abundance determined? All right. Well, the size of the current is proportional to the abundance of the ion. Right. So always got to do these. Always got to do these live, cameras. Always got to do these live, which means that the board wants to sync or doesn't sync. It's just something we just got to do. Okay. So all right. It is what it is for right now. Now then. Okay. Let's see. Just calculate the mass in kilograms of a single chromium-52 ion. All right then. So single chromium-52. This one. Can I erase a little bit? Something like this. Okay. This one here then, right? Is this one. Now, chemist, this one looks like it's kind of an easy one, right? You go, yeah, come on. Right then. But it's a bit tricky because you've got to do kilograms. Okay. And so, yes, you've got the chromium-52 ion. So if they ever ask you about the mass for an ion, it's a chromium-52 ion. Can I get this a little bit better here? I think it's doing something. Hold on. Could be in a bit of luck. Right. Just did an update. A sync, if you would. All right. Now, look. All right. Here's my chromium-52 ion. And this is 52 grams per mole. The mass of 1 mole of this ion is 52 grams per mole. All you got to do is you got to convert it over from grams to kilograms and moles to atoms. So let me do the moles to atoms first, right? So this is going to be 1 mole is 6.022 times 10 to the 23rd ions, because there's an Avogadro's number, right? That number of atoms, ions, molecules, whatever, in a mole, it's a counting unit. So moles cancel out. So now I'm in ions, and then I've just got to move from grams to kilograms. So I've got to say there's 1 kilogram in 1,000 grams. Now, chemists, I'm old school, and so I just cancel out units. Grams cancel out with grams. Moles cancel out with moles. I'm left with kilograms, and I'm left with ions. All right. So as my board updates here, okay, then let's punch this into the calculator. So I got so you got 52 divided by Avogadro's number. Okay, divided by 1,000. No, what I've got is this, is I've got 8.635 times 10 to the minus 26 kilograms per ion. Now, you're thinking, how do you know if that's right? Because rule of thumb, chemists, is that if it's out to the negative 26, 10 to the minus 26 kilograms per ion is reasonable. What I mean by that is like any calculation you do, so always could be out to about minus 10, it's always going to be out to 10 to minus 26, right? If it's 10 to the minus 23, then what you've left it in is that you've left it in grams per ion. And so you need to do one extra step. Convert to kilograms. Now then, so this was B, okay? This one, yeah, again, this one's easy, right? Other one now is the velocity. Okay, then, so, right. Well, if I got kinetic energy is 1/2 mv squared, I've got to solve for V. All right, so 2 times the kinetic energy is mv squared. And so V is going to be 2 kinetic energies over m, take the square root of it, right? Now, there you are. Plug everything in. Now, this bit, chemists, this is the bit, the tripwire, if you would. So you've got velocity is, well, 2 times the kinetic energy, which they gave you, 1.269 times 10 to the minus 13, yes, over the mass. Now, the mass of the chromium-52 ion is 8.635 to the negative 26. 8.6, was it 635? To negative 26, yeah. So on this one then, you're thinking this is not, all right, this is not 52, which is this one. Students sometimes say, oh, well, 52, right? No, it's this. You have to convert over to kilograms, okay? So here we are then. So velocity then is, if I put this into the calculator here, all right, I got 2 times 1.269 to the negative 13. Okay, and I've got to divide that by 8.635 to the negative 26. Hold on, 2.538 to the negative 13. Divide this by what? 8.635 to the negative 26. Yes, and then take the square root of that. And I'm coming back with this value here. So I got, in the calculator, it's what, 1.7. And I'm going to look by number of significant figures here. I see 4. So 1.714 times 10 to the positive, let's say 5, right? 1, 2, 3. 1, 2, 3, 4, 5, 6. 6 meters per second. Okay. Now, on this bit, did you notice how I did put in, well, number 1, units, please. And then number 2, significant figures. Always go back to the question and see what the least number of significant figures is in that question. All right. So having said that, chemists, I think we're doing pretty good. All right. So that then, let me move this up the way so you can see what's going on. Okay. This then is our first master class in the series. All right. So like I said, I hold these master classes once a week. Check in the description of the YouTube check in the description on my website. There's a section there, okay, to find out when the next masterclass is. And if you want to email me directly and say, please, could I go over a certain topic next week, then I will do so. So having said that, chemists, let's call it a wrap on this one. And you have a good day. And I will see you in the next masterclass.